Hello fellow problem solvers. So today we're going to be doing the AMC 10s, namely some problems from there to try to, learn a bit more about this competition, prep for these easier competitions where we just need to get an answer. Okay, so now without further ado, let us begin. Okay, so let's start with the problem number 1, which says, okay, we have to evaluate 9901 times 101 minus 9910. Okay, so we can actually go ahead and try to evaluate what this is actually equal to, or we can try to take a step back and see if you notice anything. Like, what are these numbers around? And you notice, well, these are numbers they're close to each other. And for me, what I think is wait a second, this is about 100 plus 1, 100 minus 1, 100 squared minus 100, 100 squared plus 100, this is both plus 1. So let's just see if we set k is equal to 100. This becomes k plus 1, and this is k squared minus k plus 1, and this becomes k minus 1, and then this is k squared plus k plus 1. And now, I'll give you 5 seconds. Do you notice anything? Well, for me, what I notice here immediately is just, wait a second, this is a difference of a sum of cubes, and this is a difference of cubes. So this is k cubed plus 1 cubed minus k cubed minus 1 cubed. The k's cancel out, and we're left with 2. And so the final answer is in fact 2. So just like that, finished. And with that out of the way, I mean, it's just we could evaluate this. We could also go ahead and say, okay, let's add, do this as 9901. We could set k to be 99 or something, but we could also do 99 times this. So we could get the 99 out. We could say 2 times 9901 plus, or actually it will be minus 99 times the difference of these two numbers. Their difference is, I think, about 200-ish. 200. So now, okay, how close are these two numbers together? Okay, you can get the 2 out. Then this is 9901 minus 99 times 100, so 9900. Oh, look, it's 2 minus 1. Again, we get a 0. There's different ways to do it quicker. I think for me, the biggest one is just like this. Seeing this thing as something roughly about 100 each. Let's go to problem 2 now. Okay, a model to hike the top of the mountain. Okay, well, this is just, it seems like a problem with AL plus BG. So what we just need to do here is plug in a system of 2 equations and figure out what's the solution when we get, we plug in some other values. So we have 69 twice. Is going to take a times 1.5 plus b times 800, and it's also a times 1.2 plus b times 1100. Okay, so you can solve this system of equations in many different ways. One way is, okay, let's subtract the 2, equalize, see what's up, and you get what? 0.3a is equal to 300b. And then what does that give us? Well, that gives us, okay, a is equal to 1000b. Okay, so now they're roughly in the same order of magnitude. So instead of a, we can write 1000b here, or instead of 1000b, we can write a. It's the same thing. We get 69 is a times 1.5 plus 0.5. So this is 23. That's why it's nice. 23 divided by 69. You get that a is, actually it's 2.3, so it becomes 30. A is 30. And then we get b is equal to, well, what? It's equal to 30 divided by 1000. And what we need to figure out, well, we need to figure out when we have 4.2 times A plus, how much are we, how long is this ascending? 4,000 times B. And now what is this? Well, 4.2 times 30, so that's 42 times 3 plus 4 times 30, which is 126 plus 120, which is 246. And so the correct answer is B, 246. So again, a system of equations like this, multiple ways to go about them. I think subtraction is a common one. When they're the same thing, you want to get rid of the constant and just have everything in terms of like A is how much B specifically, and you finish up. There isn't much I can say here really. So let's go to the next question. The sum of digits of the smallest prime that can be written as a sum of 5 distinct primes. Okay, so what's the first thing you notice? Okay, let's take this is a greedy principle type of thing. We're optimizing, so let's take the smallest ones. So we take 2, 3, 5, 7, 11. What do you notice immediately? Well, what I notice immediately is, okay, this will be odd, even, issue. So it cannot have a 2. These 5 smallest ones can't have a 2. So the smallest 5 primes, their sum is what this is, 8. This thing right here is 18. Together gives 26. And we have 39. Okay, now the question is, they have to be distinct. Can we get 41? Well, we need one of them to increase by 2, so we cannot get 41. Can we get 42? Can we get 43 is the next prime? 43, we need this to increase, one of them to increase to 4, so 17. So we have 43 is the smallest one, the sum of its digits is 7. And again, like this is a greedy sort of approach. You try the first thing, second thing, third thing, fourth thing, and see which one sticks. Not much knowledge I can really say here, except what you do in these sorts of problems, find the sum of the smallest primes. 5 distinct primes, sum. You look at, okay, the smallest one is going to have small things that add to it. Other than that, not much more to say. So let's go to the next one, problem number 4. Number 2024 is written as a sum of not necessarily distinct 2-digit numbers, okay? The least number of 2-digit numbers needed to write this sum. Okay, so again, now you're thinking about this. So 2024 is written as the sum of 2-digit number plus a 2-digit number plus some 2-digit number plus some 2-digit number, and so on and so forth. And we must find the least amount of these 2-digit numbers. So again, now you're thinking in terms of like some reasoning. If you want to use the least amount of 2-digit numbers, what numbers will you generally be using? And they don't have to be distinct. I think that's key. That makes this much simpler. Well, you're going to be using a lot of 99s. So instead of writing, say, 30 and 60, well, I can just combine these two and get a 90. So it's these like mini sort of maximization, optimization things that this is looking for. It looks for you to be able to notice these mini optimizations. So if you had 2 numbers which summed up to less than 100, you could get you can combine them into 1. Also, if you had 3 numbers, if you had numbers, say we could have, so 66 plus 66 plus 66. The question is, why write this when I could just write 2 99s instead? Again, it's about noticing these things. So, the smallest number of 2-digit numbers, okay, we're going to have 99, k times, and then we're going to have some other potentially 2-digit number. Only one of those. I mean, we could also use 98. What's it called? The least number of 2-digit numbers that we'll need. We can use some other things as well, but this will give us a clear picture of definitely we can finish with this. So now, what is 2024? Well, this is 45 squared minus 1 squared, which is 44 times 46. When you divide this by 99, you don't get it quite nicely. I always avoid these divisions. I generally don't like dividing stuff. But we get, so this is 2024 divided by 11 is going to equal 4 times 46. And then 4 times 46, we're going to say divide by 9 and roughly estimate this. Well, this is okay. This is 4 times 45, so 4 times 5 plus 4 over 9. And if I am not mistaken, I think so that means we are going to need around, this thing is now remaining. Okay, so now the floor is 4 times 5, which is 20. So we're going to have, I could have also written this as, this is not very smart of me, but I could have just seen like, hey, this is 100 minus 1 times some k. So I'm going to have 99 times 20, 20 of these. And then what remains is, okay, now I'm going to add 24, subtract and add 20. So this is 100. What's it called? Minus 1. And you want to get 2024. So you're going to need to add 44 without really calculating it, which gives us exactly 21 numbers that we need. Now you can't do it with 20. With 20 numbers, we'd get at most this number. And so we're done. Like, the answer is 21. That took actually longer than I wanted it to, but let's go on. What is the least value of n such that n factorial is a multiple of 2024? Okay, so in these types of questions, it's important to note that what is the problem really asking you? Like, what does this mean, n factorial? Something divides n factorial. What does that mean? Well, that means that the number on this side, all of its prime factors are going to show up in n factorial a sufficient number of times. What is 2024? It's 44 times 46, which is 23 times 2, 2 squared times 11. So the prime factorization is 2 cubed times 11 times 23. Always good to just know the prime factorization of your year. So what happens here? Okay, we're going to need 3 2's, a 1, and a 23 in n factorial. When do we get a 23? Well, if n factorial is at least 23. Okay, if we get n is 23, we'll get the at least 111, because it's 1 times 2 times 3, 11 times 12 times 13, till 23. And so you get your 11, you get the 2, yeah, you get 8. I mean, you have many 2's, more than you need. And that's about it. That's it. So the answer is D, 23. Let's continue onwards. Now, problem number 6. This is interesting. So you have A, B, C, D, E, F, and you need to change this to the string F, E, D, C, B, A by doing just successive swaps. Okay, of adjacent letters. This is cool. So, okay, there's like 2 ways to think about this. One is like, what does your intuition tell you? Your intuition tells you, well, if I'm just greedily moving along, and this seems to be the case here, and if you're just greedily moving along, you're gonna be fine. You're gonna get that's gonna usually be the minimum. I'll actually show proof of why that's a minimum, or like a sketch of a proof, more so. So if you're just like thinking about like, I need to move A 1, 2, 3, 4, 5 times. So 5 times for A. Then B, you're gonna need to move 4 times. C, you're gonna need to move at that point. C will be on top, in the front, so you're gonna need to move 3 times. D, you're gonna need to move twice. E, you're gonna need to move once, and so you'll need 15 turns. And you can do it in 15 terms. Is that the minimum? Okay, well, let's actually, intuitively, you'd think, yeah, here's why it is. So let's look at a function. This is going to be more advanced than the AMC 10. It's more Olympiad-like. this. Now, you don't need this, but I'm just going to show it for sake of thinking of monovariants. So a function that takes in, any sort of string and tells you the distance that A is from its optimal position. So A is from 6, plus the distance B is at from 5, plus that C is at from position 4, the distance from position 3, the distance of E to position 2, and the distance of F to position 1. Okay, let's look at this function. Initially, what is its value? Its value is, so f of a, b, c, d, e, f is going to be equal to 5 plus 5, 3 plus 3, 1 plus 1, which is equal to what? That is 18. Okay, what happens on a turn? Two numbers switch positions and everything else remains the same. So one of two things can happen. If the numbers need to go in opposite directions, then we are subtracting 2 from the function. However, if the numbers need to go in the same direction, it remains 0. And if the numbers need to go opposite directions, then you're just adding 2, which doesn't make sense. You don't need to do that. So here, you need to ask, okay, so I'm going to need to have, how many jumps will I need to have? I'll need to get A over B. I'll need to get A over C. I'll need to get B over C as well. So I'll need to have 3 moves where it's a 0 for A, B, and C. They're going to need to jump over each other when you pair them up. A is going to jump over D, E, and F, and that's going to be okay. You're going to subtract 2 from each turn. Also, mind you, this gives you a lower bound of just 9 moves. But now we're going to show that we actually need 6 other moves. And also, F needs to go over E needs to go over D, and F also needs to go over D. So there's 3 moves here as well that are going to be 0. So we're going to need a minimum of 9 moves subtracted by 2. We're going to need 3 moves that are zeros, where A goes over B, over C, B over C. 3 moves where F goes over D, E, and E goes over D. And that gives you a total of minimum of 15 moves. And that's the proof sort of why this is the case. And now let us go onwards with problem number 7. So product of 3 integers is 60. ABC is 60. And we need to figure out the least possible positive sum of these 3 integers. Okay, so the first thing that I thought here was like, okay, I just immediately implicitly assumed, and you'll see, this is 3 times 4 times 5. So implicitly I assume, okay, AMGM-like, the sum is going to be roughly smallest when these numbers are close together, so it's probably 3, 4, and 5. They give me a sum of what? They give me a sum of 12, but wait, that's not even an option. Where did I go wrong? And the answer is, okay, wait, these are integers, so they can be negative. And now you're looking at, oh, now the problem makes more sense. So that's a question of, okay, let's see so we can get 12 easily. Can we get now something lower? Okay, the positive number, if it's 20, we can have 1 positive, 2 negatives, or 2 negatives and 1 positive. So let's look at 1 positive and 2 negatives. What can we get there? So just like do case-by-case analysis here. That would be quickest for me. So what would I do here? Well, okay, we have what? Now you have, if I get 20, then the other 2 are free, so it's -1 and -3. Okay, that's one option. If it's a 10, and the positive one has to be big, you have a product of 6. It can be -3 and -2, or -6 and -1. This one gives me a sum of 3, which is one of the lowest options. And now let's see, what else do we have that we need to do, like with a case-by-case thing. If on the other hand, we have, if the big one is, so what are the factors? So 3 times 2, 3 times 2, I guess is the next one. It's a 6 here. So if we have a 6 here, we need a 10 here. We wouldn't really get anything. And now if we have just like one negative and 2 positives, then the negative can't be too large. So it can be a -6 here. And then 2 whose product is 10. Okay, that's 2 and 5. For example, actually, no, not one negative. My bad. It's not one negative. Actually, wait a second. It's either 2 negatives. Oh yeah, that does not work because that's not a product that gives us 60. So yeah, 2 negatives. Why did I think there was I guess the other case is just 3 positives, but this gives us a 3, and it's just a simple case-by-case analysis here. Nothing more, nothing fancier, and we're done. And now with this, like the other cases, just like 3 positives. And there, by the AMGM, you can think about it, A plus B plus C is greater than or equal to 3 cube roots of ABC, which is 3 cube roots of 60. And this is much bigger than 3. And that's what we needed. We have a 3 here. So let's continue onwards with new problems. So things like, okay, there's some casework going on sometimes in these problems, at least the introductory ones. Let's go onwards. A, B, C, D, work their chocolate factor. I call them A, B, C, D. I don't need to know their actual names. So A, B, and C, they start working at 1. Okay, these people finish at 2:45. So these are going to be working. So they worked how much? From 1 to 2:45. That's 1 hour and 45 minutes, 1 hour and 45 minutes, 1 hour and 45 minutes. They're able to pack, what's their rate? So 4 free and free packages every minute, every 3 minutes. Okay, every 3 minutes for everybody. So D, they can pack 5 packages every 4 minutes. Now the question is, okay, they finished packing 450 packages at this time. When did this person join the group? Okay, so in 1 hour and 45 minutes, that's 105. So all of these have sort of the same, what's it called? The same minutes. So 105 and divided by 3, you'll get that they did this in, so 35 times the sum of all of these. You had 35 times this thing was added together, which is 350 packages. And then here we have how much did this person work to be able to give us 100 packages. So they have to do 100 packages. So this is 5 in 4 minutes. To get 100 packages, they would need to work 80 minutes. So now it's 80 minus 245, which is, how do we do the clock? Do we do the clock? Well, I think it's 125. And that's about it. Again, not a lot of, there's not much here creativity. This is about just recognizing these rate types of problems, being able to solve these types of problems as well. And it's something you practice. Like I just solved this. Like I forgot when I actually did this, what the actual thing is, but I think it's just like intuitive for me. Like what's the rate? Like it's actually harder to explain if you think about it. Things that are super simple to you than things that are more advanced. Like for example, how do I explain how I multiply 11 and 17? I mean, I can explain that, but I think 11 squared, for example, I just have it memorized at this point. But let's go on to problem number 9, 2 more problems to go, and then we'll end this part of the video. So 6 juniors and 6 seniors, 3 disjoint teams of 4 people, so that each team has 2 juniors, 2 seniors. So let's think about this. So we have these 6 seniors, senior 1, senior 2, senior 3, senior 4, senior 5, senior 6. Junior 1, Junior 2, Junior 3, Junior 4, Junior 5, and Junior 6. 4 teams, each has 2 juniors, 2 seniors. Okay. Well, these teams, like, what's the question here? Like, are these teams, is it important what their names are? It seems like it's not. Well, what we can do to make things easier for us here is just say, let's call this team 1, team 2, team 3. And then whatever number we get, we will divide by 6 at the end, because the teams are indistinguishable from one another. And there's like permutations. Now, for team 1, in how many ways can I pick two of the 6 seniors? Well, I have 6 choose 2 ways to pick them. And then for each pair of seniors I pick, I have 6 choose 2 ways to pick the 2 juniors. And with that, okay, now team 1 is complete. After this, what do we have to do? Well, we have 4 choose 2 ways to pick the next 2 seniors, because 2 have already been picked. And 4 choose 2 ways there to be able to pick the next 2 juniors. These 2 things create their own branches. You can think about this as branching. We picked this pair of seniors, then we picked this pair of juniors, and then we picked this pair of seniors. We could have picked another pair of seniors. Like, there are 4 choose 2 ways to pick these seniors. Each one has their own branch. This is why we're multiplying everything through. And then you have 2 choose 2. Then you don't really have a choice for the last team. Now again, we did what? We said these are important. It's important what these teams' names are. They're team 1, 2, 3, 4, 5, and 6. But actually, that really, it doesn't really matter. Nothing really matters to me. Okay, so with the singing out of the way, what was that? Give us 6 choose 2. It's 6 choose times 4 choose 2 times 2 choose 2. Okay, that's a 1. All of this squared. 6 choose 2 is what? 3 times 5 is 15. 4 choose 2 is 6 squared. It's going to have this divided by the number of permutations of the teams, which is 3 factorial, or 6. This divided by 6. So it's 15 squared times 6 is the response, which is, what is 15 squared? I think that is about 225. I want to say 225, it's 100. So it's 10 plus 5 squared, which is 100 plus 100 plus 25, yeah, 2025 times 6. And this is equal to, so which one of the options? I think roughly it's equal to 1350. That's what the options are good for. They give you like a sense of, okay, am I on the right track size-wise? Or what's the whole thing what does the whole thing have to actually multiply through? And then you can check it out. Not much thinking there, except just like thinking about does it matter what the team's names are? If it doesn't matter, sometimes it's easier just say, okay, let's call them team 1, 2, 3, 1, 2, and 3. And then, okay, if I remove their names, it's just dividing by 6, dividing by the number of names, factorial. Okay, now with this, we are left with one more question for this part of the video, because it is getting a bit longer, and it says, consider the following operation. If n is a multiple of 3, you divide it by 3. Looks like the Collatz conjecture. If it's not, you replace it by n plus 10. So then you replace it by n plus 10. And then you continue this process. You start with 100. What value results if you perform the operation exactly 100 times? So again, so let's see what's happening with the operations to make sure we understand them. So 100 goes to 100 plus 10, 110, which goes to 120. 120 you divide by 3, and you get the number is 40. 40 goes to 50. And let's just also count these operations. Operation 1, 2, 3, 4, 5. We're not going to count up to 100, but just to see like what's happening. 60. 60, then you divide by 3. Boom. And you go down to 20. So it's operation 6. You go down to 20. 20 gets you 30. And then 30, boom, you go down to 10. And now you go to 20. Okay. So 6, then goes 20, 7, 8, 9. And then we're going to have 10, 11, 12. What do you now notice? Now it is in a what? It's in a cycle. That's exactly correct. So now just like cycling around and 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 around. The cycle length is 3. So let's see, like that means that, what's it called? So 9, 12, after move 9, after move 12, 15, 18, 99, it's going to be 20. And so after move 7, 10, 13, 16, 100, it's going to be 30. And so after you perform the operation exactly 100 times, you're going to have 30. And that is it. That's it. So that's the AMC 10A 2024, problems 1 through 10. I hope you enjoyed this little problem solving session on, these are problems that are decent in their difficulty and good little like practice. Okay. And if you're prepping for that competition, you see like there's nothing to be afraid of really. Like it's you getting sort of acquainted with these major ideas. You have permutations, the greedy sort of approach. Let me take the best one at each turn. And don't be afraid of casework. Is another thing I'll say. Don't be afraid of like just trying different cases out, testing things out, seeing what works, what doesn't work. And that's it. And as always, thanks for problem solving. Ba-doom!